Welcome! This video is optional. I know that some people get bogged down by proofs. It'll kind of get you stuck in an algebraically place that you don't need to know. But I know that for me, knowing why something works and that it does actually work is a lot more helpful than just being given a formula and asked to memorize it. So today, I'm going to talk about why a geometric series has the sum first term over 1 minus r, and why the harmonic series definitely diverges. Let's get into just a little bit of fun algebra. Feel free to skip this video if you don't like it. A geometric series in the form of c times r to the n, if it converges, right, because if r is bigger than 1, it's just going to diverge, and we know that. But if r is less than 1, then we can do this fun little proof. The sum of the series is going to be c plus, nope, that's plus. Sum of the series is going to be c plus cr plus cr squared dot 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 plus c r to the n. Right? That's just writing out what this is. Now let's do a fun little bit of algebraic manipulation. If we multiply this whole series by r, we get s times r equals cr plus cr squared plus cr cubed dot 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 plus cr to the n plus cr to the n plus 1. And you can see that this is just multiplying every term by r, but you can also see that basically we've just shifted the whole series over one term. And so what we can do now is, what if we subtract these two series? Then we're going to get s minus s times r equals, well, when we subtract these, this cancels out with this cancels out with this, dot, 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 dot. This cancels out with this, and we're left with this and this. We get c plus c minus cr to the n plus 1 equals s minus s sub r. Now, here we do a little bit of magicy, wagicky, handy, wavy stuff. Since we know that r is less than 1, and we want this sequence to go on for infinity, so this last term is basically cr to the infinity. And since we've established that the limit of this is 0, right, because r is small, and when you've got a small thing raised to the power of infinity, you get 0. So we can basically get rid of this term, because its limit is 0. So we're left with this very simple equation. If we factor an s out of this, because we want to solve for the sum, we factor an s out of this, we get s times 1 minus r equals c. And therefore, can you see the bottom of the whiteboard? Therefore, s equals c over 1 minus r, which you'll recognize as our formula. So that's why a geometric series is something that we can actually find the sum of, because there's this fun little algebraic manipulation trick that can cancel out all the terms we don't care about. And we can just get s equals c over 1 minus r. And if we want to try it out, if we want to try out this formula, prove or show, just like by evaluation, that it might work, that it probably works, if we do our good old friend 1/2 to the n, then, well, 1/2 to the n, if we're starting, as I did last time, at n equals 1, and going to infinity, of 1/2 to the n, our first term, c, is 1/2. 1/2 divided by 1 minus our r is 1/2. And so this turns into 1/2 times dividing by, this bottom is going to turn into 1/2, and dividing by a fraction is the same as multiplying by its reciprocal. So this is 1/2 times 2 over 1, which equals 1, which is what we found before. And so this little guy works, which is super fun. Now, let's switch gears and do a slightly more complex, a little bit more cerebral proof that the harmonic series, that series that is the sum of 1 minus n, or 1 over n, actually diverges, even though it looks like it totally should converge. We're going to do this one by writing out a lot of the terms. So I can say the sum of 1 over n equals 0 to infinity is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/10. And you're going to be wondering why I wrote out so many of these numbers, but it's because we can group this infinite list into an infinite number of groups of these numbers. So if we group together 1, and we group together 1/2 through 1/4, and we group together 1/5 through 1/10, you can see that we're going from n to 2n, right? So we're going from 1/2 to 1/4, 1/5 to 1/10. And we can represent this, and you can see how this could go on for forever, right? The next one would be 1/2, or 1/6, or 1/11 plus dot, 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 all the way to 1 over 22, and so on and so forth for infinity. So there are still infinity terms in this list, but we've just grouped them into like bigger terms, a little bit chunkier. And this can be written, each of these boxes, so a box equals 1 over n plus 1 over n plus 1 plus 1 over n plus 2 dot, 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 all the way to 1 over 2n. And now you do a little funky stuff. You get a little bit silly. How many terms are in this list? Well, since we're going from n to 2n, there has to be n terms within this box. There are n plus 1 terms within this box. Because in the 2 box, we have 3 terms. In the 5 box, we have 1, 2, 3, 4, 5, 6 terms. And so there are always n plus 1 terms. Wow, that's very wiggly. So in this box of n plus 1 terms, the absolute smallest of these terms is the last one, right? Because our denominator is getting bigger, which means our number is actually getting smaller. And so 1 over 2n is the smallest term we have. And so we can say that this box, the contents of this box, are at least, so are greater than or equal to, n plus 1 of that smallest term. So we know that it is actually greater than this. And what is 1 over 2n times n plus 1? Well, that is going to be 1/2 plus 1 over 2n. Right, because I've broken it up. And so what we've written is each and every one of these boxes, each and every one of these boxes has to be greater than 1/2. And if every single box is greater than 1/2, and there are infinite boxes, then we have 1/2 times infinity as our sum. And so the harmonic series, 1 over n, has to diverge. That is all. This took 10 minutes. I thought this would take like 5, but I think these are fun and useful proofs. Goodbye, all.